A common copper coin resting in a pocket or a brass door handle in a crowded terminal is often perceived as a simple, inert object of utility. Yet it represents one of the most effective and aggressive defensive systems in the known world. At the microscopic level, these surfaces are not merely cold slabs of metal, but are active, lethal environments for the vast majority of pathogens that threaten human health. While modern society relies heavily on liquid disinfectants, ultraviolet radiation, and complex filtration systems to maintain hygiene, the pinkish-red metal known as copper has been performing the same task for millennia through a purely physical and electrochemical process. This innate ability to neutralize bacteria, viruses, and fungi on contact is a phenomenon that operates with absolute mechanical certainty. Yet it remains largely hidden beneath layers of aesthetic paint or replaced by cheaper, less effective materials like plastic and stainless steel. This exploration of the material world and its hidden properties is supported by the community of thinkers who value deep inquiry. Subscribing to the channel and contributing a comment below ensures that this detailed examination of the elements continues to reach those who seek a sophisticated understanding of the physical universe. The mechanism by which copper destroys a microbe is often referred to in scientific literature as the oligodynamic effect, but it is best understood as a catastrophic electrical and chemical failure of the organism's biological systems. To visualize this process on a human scale, one might consider the outer membrane of a bacterium to be similar to a complex pressurized vessel or a high-security fortress. This membrane is maintained by a delicate balance of electrical charges and chemical gradients. When a bacterium, such as a sample of E. coli or a staphylococcus strain, lands on a copper surface, it immediately encounters an overwhelming concentration of copper ions. These ions are essentially atoms that have lost an electron and are seeking to stabilize themselves by interacting with whatever material is nearby. The copper ions act like a massive, uncontrolled power surge hitting a delicate electronics factory. They begin to punch holes in the protective outer wall of the microbe through a process called oxidation. This can be compared to a balloon being pricked by thousands of invisible needles simultaneously. The structural integrity of the cell is compromised, and its internal fluids begin to leak out into the environment. However, the destruction does not stop at the surface. Once the outer wall is breached, the copper ions flood the interior of the cell, where they begin to interfere with the metabolic machinery. They move to the cell's internal power plants and start _0_, the enzymes responsible for producing energy. Finally, the ions reach the core of the organism, where they physically bind to and shatter its DNA and RNA. This ensures that the microbe is not only dead, but is incapable of replicating or developing a resistance to the metal. Unlike antibiotics, which target specific biological pathways that a clever bacterium can eventually bypass, copper's attack is so comprehensive and multifaceted that it is effectively impossible for a microorganism to evolve a defense against it. This process occurs with remarkable speed. On a typical stainless steel surface, a colony of dangerous bacteria can survive for several days or even weeks, especially if the environment is humid. On a surface made of pure copper or high copper alloys like brass and bronze, more than 99% of these pathogens are neutralized within 120 minutes. If the surface is kept at a standard indoor temperature of 68 degrees Fahrenheit, the rate of kill is so aggressive that many viral particles are rendered inactive in as little as 15 minutes. This is a critical distinction in engineering terms. Stainless steel, while appearing _1 and shiny to the human eye, is a biological desert that allows pathogens to linger. Copper, conversely, is a biological furnace that actively cleans itself without the need for human intervention or chemical additives. The history of copper in domestic and medical settings reflects an intuitive, if not yet scientific, understanding of these properties. Ancient Egyptian medical texts, dating back more than 4,000 years, describe the use of copper vessels to store and sterilize drinking water. They observed that H2O kept in copper containers remained fresh and free of the slimes that plagued other storage methods. In the 19th century, during the cholera outbreaks that devastated European cities, it was noted that workers in copper foundries were often mysteriously immune to the disease. These observations were not the result of mysticism, but were the early recognition of a material that possesses a natural, aggressive hostility toward organic decay. In the modern kitchen, the use of copper cookware is often dismissed as a luxury or an aesthetic choice. But it is deeply rooted in the metal's superior thermal and chemical characteristics. Copper possesses a thermal conductivity that is roughly 20 times higher than that of stainless steel. In practical terms, this means that heat moves through a copper pan with the speed of an electrical signal, allowing for near instantaneous control over the cooking process. If a chef reduces the flame, the temperature of the copper drops immediately, preventing the overcooking of delicate proteins. Furthermore, the traditional copper bowls used for whisking egg whites are not just for show. The copper ions leaching into the mixture interact with the proteins in the egg whites, specifically the conalbumin, to form a stable complex that prevents the foam from collapsing. This is a form of molecular engineering occurring on a breakfast plate, where the metallic structure of the bowl dictates the physical volume and texture of the food. Despite these advantages, the mid-20th century saw a massive retreat from copper in favor of materials that were cheaper to produce and easier to maintain. Aluminium, plastic, and stainless steel replaced the red metal in plumbing, food preparation, and public infrastructure. While these materials are lighter or more resistant to tarnishing, they lack the inherent antiseptic properties of copper. The modern hospital environment, filled with plastic chairs and steel railings, has inadvertently become a reservoir for hospital-acquired infections. By covering the red hunter in layers of paint or replacing it with inert polymers, we have effectively dismantled a global, passive defense system. The cost of this shift is measured in both human lives and financial impact. A single patient suffering from a resistant infection can cost a healthcare system tens of thousands of dollars in extended care. Engineering studies have shown that replacing just 10% of high-touch surfaces in a hospital, such as bed rails, call buttons, and IV poles, with copper alloys can reduce the overall infection rate by more than 50%. This is a return on investment that few pharmaceutical interventions can match. It is the application of a material solution to a biological problem, utilizing the predictable, repeatable laws of chemistry to create a safer environment. Even the aesthetic aging of copper, the transition from a bright, polished rose to a deep brown and eventually a sea green patina, is a protective chemical process. This patina is primarily composed of copper carbonates and hydroxides. It acts as a sacrificial shield, much like the bark on a tree, protecting the structural metal underneath from the corrosive effects of oxygen and H2O. Even when the metal appears dirty or weathered, its antimicrobial effectiveness remains unchanged. The ions continue to be released, and the electrical short-circuiting of microbes continues unabated. To look at a piece of copper today is to look at a material that has been undervalued for its most vital contribution to the human story. It is not just a conductor of electricity or a decorative element. It is an aggressive biological guardian. It is a metal that works at the atomic level to maintain order and health, acting as a silent, tireless sentry against the invisible threats that populate our world. In an age of increasing antibiotic resistance and global viral threats, the simple pinkish metal of our ancestors remains the most advanced and reliable tool in our arsenal. We have spent decades trying to engineer our way around the problems of hygiene with chemicals and light, yet the solution has been resting in our pockets and under our hands for thousands of years, waiting for us to stop covering it up and let it do the work it was forged to do. The presence of copper in the Earth's crust is not a natural inevitability of planetary formation, but a rare consequence of celestial violence on a scale that defies human comprehension. While common elements like oxygen and silicon were produced in the steady, rhythmic fusion of mid-sized stars, copper represents a far more exotic and chaotic lineage. To trace the biography of a single copper atom, one must look past the birth of the sun and into the final, catastrophic moments of stars that were dozens of times more massive than any object in our current solar system. Copper is the product of stellar death, a substance forged in the specific thermodynamic conditions that exist only when a giant star exhausts its fuel and collapses under its own weight. This stellar shrapnel was scattered across the void of space billions of years ago, eventually becoming the silent, pinkish substrate of our electrical civilization. The standard life cycle of a star is a delicate balance between the outward pressure of nuclear fusion and the inward pull of gravity. In a star like the Sun, this process is relatively straightforward. Hydrogen atoms are squeezed together to form helium, releasing energy in the form of light and heat. However, as stars grow larger, they are capable of reaching higher internal temperatures, allowing them to fuse heavier and heavier elements. They create carbon, neon, magnesium, and eventually silicon. But even in these gargantuan nuclear furnaces, there is a hard limit known as the iron peak. Iron is the most stable of all nuclei. To fuse iron into something heavier does not release energy, but consumes it. This creates a thermodynamic brick wall. When the core of a massive star becomes saturated with iron, the engine of fusion stalls. Without the outward pressure of heat, gravity wins the struggle in a fraction of a second. The star's outer layers, which can weigh as much as several million Earths, crash inward at nearly 25% of the speed of light. It is in this momentary high-pressure chaos of a Type II supernova that copper is born. As the star's material is crushed against the ultra-dense core, a massive flux of neutrons is released. These neutrons act like subatomic projectiles, slamming into existing iron and nickel atoms with such frequency that they are absorbed into the nucleus before the atom has a chance to decay. This is known as the R process, or rapid neutron capture. It is a form of cosmic alchemy where the sheer density of energy allows the laws of standard stellar chemistry to be bypassed. The temperature in these final seconds exceeds 100 billion degrees Fahrenheit. In this furnace, the atomic number of the matter is pushed upward, jumping past iron, 26, and cobalt, 27, to reach the 29 protons required to define the element as copper. Without these rare and terminal explosions, the universe would be a place of heavy iron and light gases, devoid of the conductive metals necessary for complex electronics. The distribution of this newly forged copper into the cosmos is equally violent. The supernova explosion hurls this material into the interstellar medium at speeds of thousands of kilometers per second. For hundreds of millions of years, this copper-rich dust drifts through the vacuum of space, mixing with giant clouds of molecular hydrogen. These clouds are the nurseries of future solar systems. When our own solar system began to coalesce approximately 4.5 billion years ago, it was already seeded with the copper shrapnel of long-dead stars. As the early solar nebula spun and flattened into a disk, the heat of the forming sun pushed the lighter gases toward the outer regions, while the heavier metallic dust remained in the inner ring. This is why the terrestrial planets, Mercury, Venus, Earth, and Mars, are rocky and metallic rather than gaseous. However, the fact that we can mine copper at the Earth's surface today is a secondary geological miracle. During the early molten phase of Earth's formation, the planet was a roiling sphere of liquid rock and metal. Elements that are quote, _8, or iron-loving, such as gold and platinum, dissolved into the molten iron and sank to the core, becoming forever inaccessible to human industry. Copper is quote, _9 ___, meaning it has a strong chemical affinity for sulfur rather than iron. As the Earth cooled and the first continents began to stabilize, copper did not sink to the core in its entirety. Instead, it bonded with sulfur and moved through the mantle and crust in hydrothermal fluids. These fluids are essentially superheated H2O, saturated with dissolved minerals and circulating at pressures high enough to fracture solid rock. To understand this process, one could look at the Earth's crust as a giant, pressurized filtration system. As magma rises toward the surface in volcanic regions, like the Andes Mountains in South America or the Copper Belt in Africa, the cooling process causes minerals to precipitate out of the liquid. Copper is often deposited in __quote_10__ systems, massive, low-grade concentrations where the metal is dispersed through huge volumes of rock like tiny raisins in a colossal loaf of bread. Over millions of years, the slow work of tectonic uplift and the relentless erosion of wind and rain strip away the overlying mountains, bringing these deep, copper-rich deposits close enough to the surface for human discovery. The quantity of copper on Earth is estimated at roughly 10 to the 14th power tons, yet most of it is spread too thinly to be useful. The history of human technology is essentially the history of finding the rare places where the Earth has done the __quote_11____ for us. In the Atacama Desert in Chile, the absence of rainfall for millions of years has allowed copper minerals to accumulate in thick, concentrated layers that would have been washed away in more humid climates. These deposits are the result of a specific geochemical coincidence: the subduction of an oceanic plate beneath a continental plate, the presence of sulfur-rich magma, and a climate that preserved the result. The physical properties of the copper atom itself are a reflection of this high-energy origin. With 29 protons and a single loosely bound electron in its outermost shell, copper is the ultimate conductor of both heat and electricity. This outer electron is __quote_1_2____ to move from one atom to another with minimal resistance. In a copper wire, these electrons behave less like solid particles and more like a fluid, flowing through the lattice of the metal like H2O through a pipe. This fluidity is what allows copper to transmit information and power across vast distances with near-perfect efficiency. It is a material that was designed in the heart of an exploding star to be the bridge between energy and matter. When humanity first began to hammer at native copper nuggets in the Middle East 10,000 years ago, they were unknowingly interacting with the leftovers of a galactic catastrophe. They were using a material that was too heavy for our own sun to create, a substance that had survived a journey through the light years of the interstellar void. The pinkish glint of a copper vein in a mountainside is a direct message from the deep past of the universe. It is a reminder that the tools of our modern life, the sensors in our cars, the wiring in our homes, and the processors in our pockets are constructed from a material that required the total destruction of a giant star to exist. We live on a planet that has acted as a cosmic filter, trapping this stellar ash in its crust and concentrating it through millions of years of volcanic activity, just so that a biological species might one day use it to tame the power of the electron. The __quote_13__ nature of copper is perhaps its most profound characteristic. It is a gift from the most violent events in the universe, delivered to a cooling planet and hidden just beneath the soil, waiting for the first inquisitive mind to pick up a stone and realize it could be shaped into something more. The human transition from the Stone Age to the era of metals was not merely a change in tools, but a fundamental shift in the species' relationship with the material world. For hundreds of thousands of years, the pinnacle of technology was the sharpened edge of flint or obsidian, materials that were brittle and unforgiving. The discovery of copper represented the first time humans encountered a substance that could be shaped, melted, and reformed without breaking. This era, known as the Chalcolithic or the Copper Age, began approximately 7,000 years ago and turned the soft, pinkish metal into the ultimate measure of social and military power. To a person living in a world of bone and rock, a copper tool was a device from the future, possessing a degree of durability and repairability that seemed almost supernatural. The reality of this prestige is most vividly captured in the discovery of the Tisenjok mummy, popularly known as Utsi the Iceman, who lived around 3,300 BC. When his preserved body was found in the Italian Alps in 1991, he was carrying a toolkit that redefined our understanding of ancient technology. His most significant possession was a nearly pure copper axe, consisting of 99.7% copper. In the social hierarchy of the 4th millennium BC, this axe was the equivalent of a top-tier modern smartphone or a high-performance vehicle, a high-status gadget that signaled the owner's access to a complex and expensive supply chain. To produce such an object required a chain of engineering that spanned hundreds of miles. The copper had to be mined from deep ore deposits, crushed, and then subjected to a process of smelting that was the high-tech industry of its day. Smelting copper is an exercise in thermodynamic management. Unlike gold, which is often found in its pure state, copper is usually locked in minerals like malachite or azurite. To extract it, ancient smiths had to create a controlled environment where temperatures reached at least 1,984 degrees Fahrenheit. This was achieved using charcoal and hand-operated bellows to force oxygen into a furnace, a process that required a deep understanding of air-to-fuel ratios, long before the laws of chemistry were written. The charcoal acted as a reducing agent, stripping the oxygen away from the copper ore to leave behind molten metal. This was the first time humanity successfully manipulated the internal atomic bonds of a mineral to create a new material. The copper axe was not just a weapon, it was a physical manifestation of human mastery over fire and chemistry. It could be sharpened indefinitely, and if it broke, it could be melted down and recast into a new form, a concept of recycling that was impossible with stone. As civilizations matured, copper's role evolved from individual status symbols to the foundation of global geopolitical dominance. By the 18th century, the metal became the secret weapon in one of the greatest naval arms races in history. During this period, wooden warships were the primary instruments of imperial power, but they faced a relentless biological enemy, the Teredo navalis, or the shipworm. Despite its name, this creature is a wood-boring bivalve mollusk that can grow up to 2 feet in length. It functions like a biological drill, riddling the hulls of ships with thousands of microscopic tunnels until the structural integrity of the timber is compromised. Furthermore, marine growth like barnacles and seaweed would attach to the underwater portions of the ship, creating a massive amount of drag. A ship encrusted with biofouling could lose up to 30% of its speed, making it sluggish in maneuvers and incapable of outrunning an opponent. For decades, navies attempted to protect their ships using mixtures of tar, hair, and even lead sheathing. Lead was heavy and prone to falling off, while tar was easily eroded by the motion of H2O. The British Royal Navy began experimenting with copper sheathing in 1761 on the frigate HMS Alarm. The results were transformative. Copper provided a dual-layered defense. First, it was a physical barrier that the shipworm could not penetrate. Second, and more importantly, the copper reacted with the salt water to create a toxic environment for marine organisms. As the seawater, which is a mixture of H2O and various salts, interacted with the copper, it released a constant stream of copper ions. These ions acted as a powerful biocide, preventing the larvae of barnacles and mollusks from ever attaching to the hull. The engineering of this copper-bottomed fleet gave the British Navy a decisive technological advantage over the French and Spanish fleets. During the American Revolutionary War and the Napoleonic Wars, British ships could stay at sea for years without needing to be hauled into dry dock for cleaning. Their vessels were faster, more maneuverable, and more durable than any others on the ocean. However, the adoption of copper sheathing introduced a new and unforeseen engineering problem: galvanic corrosion. The early copper sheets were held in place with iron nails. In the presence of salt water, the copper and iron formed a massive accidental battery. Because copper is a more noble metal than iron, the iron nails acted as an anode and began to dissolve rapidly into the H2O, leading to the copper sheets falling off and the ships nearly falling apart. The solution to this problem was a masterpiece of 18th century material science. To prevent the electrical leakage between the two metals, shipbuilders began to use copper or brass nails and inserted a layer of thick paper or animal hair soaked in tar between the wood and the copper. This created a primitive but effective electrical insulator. This copper bottoming was so successful and so synonymous with quality that the term entered the English language as a metaphor for a venture or an object that is absolutely reliable and certain to succeed. It was the first time a single element was used on an industrial scale to control the biological environment of a machine. This period also marked the beginning of intense industrial espionage centered on copper. The secret of how the British managed to produce large, uniform sheets of copper and the specific alloys used for the nails was a matter of national security. French spies were sent to British copper mills to observe the rolling processes and the composition of the furnaces. The ability to refine copper at scale became the defining characteristic of a superpower. It was not just about the gold in the treasury, but about the copper on the hulls and the brass in the cannons. Copper was the material that allowed the British Empire to project power across the globe, effectively shrinking the world by increasing the speed and reliability of naval travel. However, as the 19th century progressed, the role of copper shifted from the surface of the ocean to the invisible realm of electromagnetism. The discovery by Michael Faraday and others that a moving magnetic field could induce an electrical current in a copper wire changed everything. Suddenly, the metal that had been used for axes and ship hulls was needed for something entirely new: the transmission of information. The telegraph was the first internet, and its physical body was made of copper. In 1858, when the first transatlantic telegraph cable was laid between Ireland and Newfoundland, it represented an engineering feat equivalent to the moon landing. Thousands of miles of copper wire had to be manufactured to an unprecedented level of purity, and then insulated with gutta percha, a natural latex, to prevent the signal from leaking into the H2O of the Atlantic. The historical drama of copper is a story of a material that kept finding new ways to be indispensable. We moved from the prestige of the copper axe to the dominance of the copper-bottomed fleet, and finally to the connectivity of the telegraph wire. Each step required a deeper understanding of the metal's atomic and chemical properties. Copper was the catalyst that took humanity out of the isolation of the Stone Age and began the process of weaving the world into a single, interconnected organism. It was the material that taught us how to smelt, how to navigate the oceans, and how to talk across the void of space. The pinkish metal, once valued for its beauty and its edge, had become the silent conductor of the modern world's first global network, proving that the true value of an element lies not in its rarity, but in its ability to adapt to the changing needs of human ingenuity. The physical reality of the modern world is supported by a sprawling, intricate lattice of copper that functions as the primary nervous system of human civilization. While the visible architecture of cities is defined by steel, concrete, and glass, the invisible flow of energy and information, the lifeblood of every modern activity, is entirely dependent on the specific atomic properties of the 29th element. Copper occupies a unique position in the hierarchy of materials because it possesses the highest electrical conductivity of any non-precious metal. To understand the magnitude of this advantage, one must look at the movement of electrons through a solid.
In most materials, an electrical current is like a crowd of people trying to move through a room cluttered with furniture. The electrons constantly collide with atoms, losing energy as heat and slowing the flow. In copper, however, the atomic structure is like a wide, polished, and empty hallway. Because copper has a single, loosely bound electron in its outermost shell, these electrons can slide from one atom to the next with almost zero friction. This efficiency is the fundamental reason why the global energy transition, the rise of artificial intelligence, and the electrification of transport are physically possible. The role of copper in the Green Revolution is perhaps the most significant engineering challenge of the current century. An electric vehicle, EV, is not merely a car with a different engine. It is a complex mobile electrical plant that requires a massive increase in conductive material. A traditional internal combustion engine vehicle contains approximately 20 kilograms or 44 pounds of copper, used primarily for the starter motor and basic wiring. In contrast, a high-performance electric vehicle, such as a Tesla or a modern electric bus, can contain between 80 kilograms and 100 kilograms of copper. This four-fold increase is necessitated by the physics of the electric motor and the battery pack. Inside the motor, copper is wound into tight, dense coils known as the stator. When an electrical current passes through these coils, it creates a powerful magnetic field that drives the rotation of the engine. The efficiency of this motor is directly tied to the density and purity of the copper. If an engineer attempted to use aluminium to save weight, the motor would have to be significantly larger to achieve the same power, because aluminium is only about 60% as conductive as copper. Copper's superior ductility, its ability to be drawn into wires as thin as a human hair without snapping, allows these coils to be packed into the incredibly tight spaces required for automotive performance. This dependence extends to the infrastructure that supports these vehicles. A single high-speed charging station requires massive copper cables to handle the intense flow of current, often delivering hundreds of kilowatts of power in a matter of minutes. At these energy levels, the resistance of the cable becomes a critical safety and efficiency factor. If the resistance is too high, the cable will generate immense heat, reaching temperatures that could melt plastic insulation or even trigger a fire. Copper's ability to move these massive quantities of electrons while remaining relatively cool, a property governed by Ohm's law, makes it the only viable material for the fast-paced energy demands of the 21st century. Without a steady supply of this metal, the dream of a carbon-neutral transportation network remains a physical impossibility, as no other material can match copper's combination of conductivity, thermal stability, and mechanical strength. The digital world, often perceived as a realm of ethereal data and cloud computing, is in reality a massive industrial consumer of copper. Every data center, the massive warehouses of silicon and cooling fans that power the internet, is a concentrated hub of copper connectivity. While long-distance data transmission relies on fiber optic cables, the last inch of the internet, the connection between the server, the processor, and the power supply is almost exclusively copper. On a printed circuit board, PCB, copper is etched into microscopic pathways that are hundreds of times thinner than a human hair. These traces must carry high-frequency signals with absolute precision. Any impurity in the copper would cause signal degradation or noise, resulting in data errors and system crashes. Furthermore, the immense heat generated by modern processors must be dissipated rapidly to prevent the silicon from melting. Copper heat pipes and heat sinks are used because copper conducts heat with an efficiency of 400 watts per meter Kelvin,
which is nearly twice as effective as aluminum. It acts as a thermal sponge, soaking up the waste energy of 1 billion calculations and moving it away from the delicate heart of the computer. The generation of renewable energy is another area where copper acts as a silent but essential driver. A single 3 megawatt wind turbine requires approximately 4.7 tons of copper to function. This metal is found in the massive generator at the top of the tower, in the heavy-duty transformers at the base, and in the miles of underground cabling that connect the turbine to the electrical grid.
Solar power follows a similar pattern. A typical solar installation uses 5.5 tons of copper per megawatt of capacity. The logic of the green economy is simple. To capture energy from diffuse sources like wind and sun, one must use a larger volume of conductive material to collect and transport that energy. This creates a fascinating industrial paradox. To reduce the world's reliance on carbon-intensive fuels, humanity must drastically increase its mining and processing of copper. The __quote_32_ is not found in a new exotic gas, but in the intensified use of a pinkish metal that has been known to humans for 7 millennia. The efficiency of a power grid is determined by the __quote_33__, the amount of electricity that simply vanishes as heat while traveling from the power station to the home. In a world with a high-resistance grid, this loss could be as high as 10% or 15% of all energy generated. By using high-purity copper in transformers and distribution lines, this loss is minimized. This is an engineering necessity governed by the relationship between cross-sectional area and resistance. To lower the resistance of a wire, one must either increase the thickness of the wire or use a more conductive material. Copper provides the perfect balance of these factors, allowing for the construction of a grid that can span entire continents while wasting as little energy as possible. In a very real sense, the stability of modern society, the fact that lights turn on instantly and hospitals remain powered, is a direct result of copper's ability to manage the chaotic movement of electrons at a planetary scale. Even the transition to smart infrastructure is a copper-intensive endeavor. The Internet of Things, IoT, which envisions a world where every appliance, streetlight, and factory machine is interconnected, requires a massive expansion of electrical wiring and sensors. Each of these sensors contains a copper-based antenna and microcircuitry. The smart home of the future is essentially a home wrapped in a denser, nervous system of copper, allowing for the precise control of heating, lighting, and security. The more intelligent our environment becomes, the more copper it requires to facilitate the flow of data that constitutes that intelligence. The physical durability of copper also plays a role in its modern utility. Unlike iron, which oxidizes into a flaky, structurally weak rust in the presence of H2O and O2, copper develops a stable patina. This means that copper wiring buried in a wall or a subterranean conduit can remain functional for 50 to 100 years with minimal degradation. This longevity is crucial for the reliability of the global infrastructure. It means that the investments made in the electrical grid today will serve the next 3 or 4 generations. This set-it-and-forget-it characteristic allows engineers to build complex, hidden systems that function silently in the background of human life, only becoming noticeable in the rare event of their absence. Ultimately, copper is the material that has turned the Earth into a single, interconnected machine. It is the bridge between the raw energy of nature, whether captured from a spinning turbine or a silicon wafer, and the human desire for light, heat, and information. It is a metal that possesses an almost miraculous level of utility, functioning with the same reliability in a 1000°F industrial furnace as it does in the frozen vacuum of a satellite circuitry. Copper does not want to conduct. It simply follows the laws of physics with a precision that allows us to build a predictable, high-tech reality. Without this nervous system, the modern world would go dark and silent, reverting to a collection of isolated communities separated by the insurmountable resistance of a world without a universal conductor. Copper is the silent architect of our synchronicity, the element that allows 8 billion people to live, work, and communicate in a single, high-speed global organism. The long-term trajectory of human presence on Earth will be measured not by the survival of biological records, but by the chemical persistence of the materials we have extracted, refined, and distributed across the globe. Among the suite of elements utilized by modern industry, copper possesses a unique capacity for noble aging, a characteristic that ensures its survival long after organic structures and ferrous metals have returned to the state of dust and rust. While iron is a victim of its own chemistry, expanding and flaking away into a brittle orange powder when exposed to H2O and oxygen, copper participates in a process of self-preservation. When a copper surface is exposed to the atmosphere, it does not simply decay. It constructs a sacrificial armor through a series of complex chemical reactions that evolve over decades. This is the phenomenon of the patina, a sea green or dark brown layer that acts as a mineralogical seal, effectively pausing the passage of time for the metal underneath. To understand this chemical defense, one must analyze the progression of the metal's interaction with the environment. Initially, a polished copper surface reacts with oxygen to form a thin layer of copper oxide. This is the stage where the metal loses its rose-colored luster and turns a deep chocolate brown. Over years, as the metal is subjected to rainfall containing dissolved carbon dioxide and sulfur compounds, this oxide layer is converted into more stable minerals: brochantite, malachite, and azurite. These are the same minerals found in geological copper deposits. In effect, the metal is turning its outer surface back into stone. This mineral skin is incredibly dense and adheres tightly to the atomic lattice of the copper. It prevents additional oxygen, or H2O, molecules from reaching the fresh metal underneath. In a temperate climate, this process can take 20 to 30 years to reach equilibrium, resulting in a protective layer that is only a few thousandths of an inch thick, but is capable of preserving the structural integrity of the metal for centuries. The Statue of Liberty, which was inaugurated in 1886, serves as a primary engineering case study for this durability. Despite being encased in a skin only 2.4 millimeters thick, roughly the thickness of 2 pennies stacked together, and being constantly battered by the salty, corrosive air of the Atlantic, the copper remains structurally sound. The green patina has acted as a permanent, maintenance-free preservative, ensuring that the monument will likely remain standing long after the iron framework inside has required total replacement. This characteristic of permanence leads to a second, more industrial paradox. Copper is one of the few materials on Earth that can be described as truly immortal through the process of recycling. In a world defined by the planned obsolescence of electronics and the degradation of plastics, copper stands as a circular asset. It is estimated that at least 80% of all the copper ever mined by humanity, dating back to the first smelting fires of the Copper Age, is still in productive use today. This is because copper does not lose its physical or chemical properties when it is melted down. In a recycling facility, a discarded computer cable and a 5,000-year-old decorative ornament can be melted together in a furnace at 1,984 degrees Fahrenheit. The impurities are skimmed off as slag, and the resulting molten liquid is as pure and as conductive as if it had just been extracted from a primary mine in the Andes. The thermodynamics of this process are highly efficient. Recycling copper requires only about 15% of the energy that is needed to mine and refine new ore. From an atomic perspective, the lattice of copper atoms is incredibly resilient. The sea of electrons that allows for conductivity is not disrupted by the transition from solid to liquid and back to solid. This makes copper a permanent part of the global inventory.
Every time a new data center is built or a new wind turbine is erected, there is a high probability that the copper within its wiring has a multi-generational history, perhaps having once been a part of a 19th century telegraph line, a Renaissance-era bronze cannon, or a Roman water pipe. Copper is the most honest biographer of our technological evolution, a material that is constantly being reshaped but never diminished. When we project the legacy of the 21st century into the deep future, thousands or even millions of years from now, the role of copper as a techno-fossil becomes clear.
If humanity were to suddenly disappear, the cities of concrete and glass would eventually collapse. The steel skeletons of skyscrapers would oxidize and crumble into iron-rich soil within a few centuries. Plastics, despite their reputation for longevity, would be broken down by ultraviolet radiation and microbial action into microparticles and eventually into their constituent carbon chains. However, the buried infrastructure of the electrical grid, the thousands of miles of copper cables encased in lead or buried deep within subterranean conduits, would remain. These would become the stratigraphic markers of the Anthropocene. Future geologists, whether they are descendants of a renewed human species or visitors from another world, would find anomalous veins of high-purity copper running through the sedimentary layers of ancient landfills and city ruins. These wires would not resemble any natural mineral formation. They would be long, uniform, and composed of a purity level that does not occur in nature without industrial intervention. These buried networks would reveal the true extent of our civilization's reach, tracing the pathways where energy once flowed to power the digital age. They would be the silent metallic nervous system of a vanished global organism, a permanent record of a species that learned to organize the matter of the universe into a functional, conductive network. The final chapter of copper's biography on Earth is dictated by the inevitable life cycle of the Sun. Approximately 5 billion years into the future, as the Sun exhausts its hydrogen fuel, it will expand into a red giant. The temperature of the Earth's surface will begin to rise toward 1,000 degrees Fahrenheit, and eventually, as the Sun's outer atmosphere nears the planet's orbit, the surface will exceed 2,000 degrees Fahrenheit. At this threshold, the melting point of copper will be reached. The entire infrastructure of our era, the cables, the statues, the hidden wires, will liquefy and pool in the depressions of a scorched landscape. As the Earth is eventually consumed by the solar atmosphere, the copper atoms will be vaporized. They will return to the state of gas and dust, drifting once again into the interstellar medium. In this cosmic perspective, the time copper spends on Earth and within human hands is merely a brief, orderly interlude. The atoms of copper that we use to charge our phones or drive our cars are the same atoms that were forged in the death of a distant star billions of years ago, and they are the same atoms that will eventually witness the death of our own sun. Copper is a material that transitions from cosmic chaos to industrial order, and back to cosmic chaos without losing its identity. It is the 29th element, a soft, pinkish metal that proved to be the most reliable conductor of human progress. It allowed us to conquer the darkness with light, to bridge the distance between continents with information, and to protect our health with its lethal efficiency against the microbial world. When the story of Earth is finally concluded, the copper atoms will be among the last witnesses to the end, having survived the entire duration of the planet's existence. They will be scattered back into the void, potentially to be pulled into the gravity of a new nebula, to seed a new solar system, and perhaps to be picked up by another inquisitive mind in a different corner of the galaxy. Copper is the ultimate traveler, an element that has moved through the hearts of stars and the networks of a global civilization, proving that the most profound forces in the universe are often found in the most humble and familiar of objects. It is the red vein of the cosmos, the silent partner in every endeavor that requires the movement of energy,
and the most durable monument to the brief moment when humanity held the lightning in its hands.